v2.1. Is it a must-have or is it a deal breaker for us? So let's jump right into the topic. First of all, for those who just vaguely know, PTP is an IEEE standard under the number of 1588, and it describes a protocol for transferring time accurately through data networks. So we can achieve sub-microsecond time and frequency accuracy. It's a highly generic standard, so it is not just related to our media industry. In contrary, it's been used by a wide range of time-sensitive applications, the wider industry. So we have telecom power, finance, industrial automation, medical, actually, that's where it originated from in the early days. So quite a huge amount of different industries is relying on time transfer by 1588. We have currently 3 versions of 1588, the initial version being published in 2002, known as PTP version 1. Then we had the most common version. I was about to say the current version, but the current version is now the latest version. But the most common version is the 2008 version, PTP version 2. And the latest version has been published in 2020. We just spoke about the time it takes from finishing the standard, which actually is 2019, but it wasn't published before some month into 2020. You know, that's procedures. So that's what it's about. Just a quick recap. PTP version 2 is the basis for our SMPTE 2110 protocol for our media over IP networks industry. And just a very, very quick recap. We use PTP for media and stream clock generation and synchronization. So we have usually a master clock in the system. And as you can already see, 2110, SMPTE 2110 drafting group is trying to replace all insensitive and maybe discriminating language into other words. So they decided to change master clock into leader clock. Likewise, we have slave clocks, which are now called followers. And those are synchronized through the PTP protocol to follow the leader exactly enough. And from the local copy of time, media clocks are generated locally on the individual devices. So if you look into a pair of individual devices, again, we have the Grandmaster clock. By the way, Grandmaster as a term hasn't changed, so we'll still call it Grandmaster. And we have a sender and receiver device with their local clocks, and we have a PTP protocol which copies basically the exact Grandmaster time into the local clocks of the participating devices. Then the media clocks are generated independently in each device by referring back to the local PTP clock copy of the Grandmaster. That happens in the receiver as well. And then a sender can generate a stream with an individual RTP stream clock, but that is bound back to the media clock or to the local copy of the PTP. So the RTP stream clock basically follows the PTP or is generated out of the PTP Grandmaster clock. Now, as you can see, here's a random offset between the RTP stream clock and finally the local clock in the sender. That offset R has been defined by the underlying standard, which is RFC 3550, to be random per individual stream. But it's constant throughout the lifetime of the stream, and the offset will be conveyed out of band to the receiver, which needs to know, of course, the offset in order to align the incoming stream with its local clock. That's through means of SDP transfer. And 2110 has the speciality or the constraint set forth that the random offset R is to be eliminated by lining it up with a 0 offset with respect to the Grandmaster clock or the media clock reference. So that is how 2110 and PTP version 2.0 work in our industry to generate media clocks and synchronize. And we have another standard which is very important, which is the SMPTE SD 2059 standard suite of network delivered references. It's a -1 document which talks about the epoch and the signal generation, so about all the alignment points, the calculations and algorithms which are required. And more important, the -2 document defines a particular SMPTE PTP profile, which sets forth specific rules required for the SMPTE applications, specific SMPTE metadata, and all the necessary network and operating parameters like the message rates, as you can see here in the table, just the most important message rate. Here's a quick remark. As you can already see, the default announce interval in the existing -2 document was at 250 millisecond. And the revision, which is currently in its final stages, in the revision, they decided to set the default value to 1 second for the announce message for better better interoperability with other existing PTP profiles like the IEEE 67 media PTP profile and the default profile of the PTP standard itself. So then let's have a quick look at PTP compatibility, because that's a big issue, of course. Now, when PTP was released with its first version in 2002, of course, there was no backward compatibility. It was just the standard as being set forth by the document, by the standard committee. And then in 2008, they released version 2. And the problem is there is no backward compatibility to version 1. So you can use PTP version 2, but PTP version 1 devices cannot participate in the version 2 protocol and vice versa. Particularly, this is important not just for end devices, but also for network PTP-aware network devices like boundary clocks and transparent clocks. So they can either talk PTP version 1 or version 2. So then 2019, we saw PTP version 2.1. And of course, the question is, will it break compatibility with our precious 2110 and 2059 standards? The main message here for today is don't panic. It is fully backward compatible with version 2 as of 2008. And that is because through the experience the IEEE working group had with its non-existing backward compatibility between 2 and 1, the prerequisite for a new standard basically was to preserve backward compatibility with whatever they will come up with. So backward compatibility, just as a summary again, means that any version 2.1 device, which are leaders, followers, or boundary clocks, transparent clocks, work in PTP version 2 networks and won't compromise it. All the version 2.1 features are optional, so they are add-ons, and PTP version 2 features work as before with all the PTP version 2.1 equipment. That's the important message. So we can all go and relax and see actually what is in PTP version 2.1. So let's have a look. What has been added? What is new in PTP version 2.1? Basically, we can group the additions, amendments into 4 categories. As always, some things just make the existing standard clearer, removing ambiguity, adding some explanations. Then features have been added for more flexibility. Other features address robustness of the protocol, and also accuracy options have been added so for achieving increased accuracy. And as I have already told you before, some, if not the majority of those features which have been added to the protocol standard were taken from already existing PTP profiles. So just a few features have been taken out of the wild. Everything else had been used in other applications with other profiles in particular environments, and was therefore proven to be working enhancements. So let's address flexibility first. So what features have been added to the standard in order to increase the flexibility? One very, very important feature is that now mixed multicast and unicast operation is part of the standard. You could have done multicast and unicast operation before, but on a way which required quite a lot of configuration and engineering. And now mixed multicast unicast operation is part of the standard as an operational mode. So that means that announce and sync messages are sent out by masters or the grandmaster through multicast, and all the delay request and delay response messages can be sent or transported in unicast. This is, of course, addressing better scalability, particularly in larger systems, which use end-to-end synchronization. So in order to achieve this, new TLV blocks have been added to the announce message, and new multicast messages had been added to inform the system about the particular unicast addresses for such case. Next thing, for adding flexibility, modular transparent clocks have been defined. That provides the ability that transparent clocks can now be built in blade servers or into an SFP architecture, due to the fact that the stepness has now moved over to being a port property instead of a clock property. So now this sounds, for those who are not very deep into the topic, sounds a bit weird. Basically, the stepness defines or describes if sync messages, for example, are sent out in one-step or two-step mode, where the actual timestamp is being either imprinted in the sync message itself or being sent afterwards to tell a receiving device, well, that sync message you just received had been sent out at that particular stage. And with that being a property of a clock, of a PTP clock instance before, there were difficulties in actually adding transparent clock functionality into plug-in SFPs and basically other ports. So that is behind the capability of modular transparent clocks. Then as a next step, special PT ports have been added to the definition of the PTP standard. The reason here is that some of the technologies which have been used to transport PTP messages have their own built-in timing mechanisms, like EPROM, Wi-Fi, or other technologies. And for being able to make use of this built-in timing mechanisms to work together hand in hand with these built-in timing mechanisms by defining special PTP ports, this can result in better stability and accuracy of PTP being transported over such type of networks. The next big area is robustness. Features have been added to increase the robustness of the PTP protocol. First thing to mention is profile isolation. Theoretically, you were already able to run different profiles on the same network. So let's say a default profile, an AS67 media profile, the SMPTE 2059 profiles, or even other profiles, which was addressed through using different domain numbers for those individual profiles. But it turned out that this is a tedious configuration work, and also in some cases resulted in errors because people didn't pay much attention with the domain number configuration, or even on the end node side by evaluating the domain number for incoming messages. So that has been added through profile IDs, which are assigned to particular profiles of standardization organizations. It's called the SDO ID. This is a fully backward compatible step which uses previously reserved fields in PTP header messages. So if you look at a PTP version 2 header message, compare it to a PTP version 2.1 header message, you see the size hasn't been changed. All the fields which were not reserved are in the same place. And the SDO ID is making use of the reserved fields from the version 2.0 header by adding information into those fields. So that's full backward compatible process, because version 2.0 devices which are not aware of these SDO IDs just ignore it and work as they did before. Next thing is the interdomain interaction. Running multiple domains on the same network has already been an option, but with the enhanced features of this addition, you can now build slave clocks or ordinary clocks which reside or are being built as multi-domain clocks for receiving information from different grandmasters, basically serving the same time, of course. So we have individual grandmasters on the network. They're all sending out their sync messages into the network using different domains. We have a multi-domain clock. That's something which can be built now, which has a singular link into the network, which also introduces another feature of PTP version 1, the common mean link delay service, where that multi-domain clock can have one link delay measurement instead of 3 for all these individual clocks. Of course, the individual clocks talk to their grandmasters, receive time from their grandmaster, and through a voting algorithm or mean value algorithm, whatever is built in there, you can build a very, very robust and precise clock with a resulting time. Now, if one of those clocks fails, just like the GM3 in this example, the voting algorithm would detect that this is not serving the same time as the other two, and so it's out of the algorithm, and the robust clock still works, serving the time built from OC1 and OC2. So that is an option which is now available in PTP version 2.1. Security was a big point in the discussion. Security has been added security features. First of all, in the standard, you will find now security guidelines, which have not been part of the version 2 specification. But even more important, the committee has added authentication TLVs for messages, plus a source integrity checking value at the end of the message, so that now a PTP message can be cryptographically signed, and the slave can actually detect if the message just received is actually coming or is actually authenticated and coming from the expected source. So rogue message insertion can now be detected, and those messages can invalidate it on the slave side. Another important feature is the introduction of standard performance metrics. Of course, everybody was able to, display the precision and accuracy and whatever parameters are important on slave clocks before this, but wouldn't it be better to have a standard which is equal for all the slave clocks? So the committee defined a standard format for performance statistics, which includes average, min, max, and standard deviation values of the most important parameters, which are offset from master and other various delay metrics. It also introduces a message reception counter so that you can detect missing messages. And all of this is being recorded for 50 minutes intervals within 24 hours. So that results in a number of something like slightly below 100 values, which have to be permanently sampled and updated in a slave clock, and then they can be called through a standard or by a standard format by a management device. Also in the same direction is active slave port monitoring, which would now allow not only to passively call for the performance statistics, but also forward messages to a monitoring device, which is then able to monitor the sync timing and the computed data in a particular TLV, as well as the event timestamps when a slave is sending out delay request messages, for example. So that can be actively forwarded to a monitoring instance now. So this has all been added in terms of robustness to the standard. And the final field where they had been working on added features is accuracy. And basically all of these features originated from the so-called White Rabbit project. At the very beginning of PTP 2008 or 1588-2008, PTP version 2.0, some people at CERN in Geneva needed higher accuracy, and so they developed developed enhancements to the PTP version 2.0 standard in order to increase the achievable accuracy into a sub-nanoseconds accuracy. And that project was called White Rabbit. And basically all of the White Rabbit extensions have been found or have found their way into the PTP version 2.1 optional feature extensions. So one of those is manual port configuration. As you all know, in our networks, we have the best master clock algorithm where the network configures itself, where the best available master is or grandmaster is detected. And it dynamically changes the configuration if the grandmaster fails and so on. And now this is not very productive if you want to have very quick startup of network timings and very precise timing, which does not is not allowed to change occasionally or just by chance all the way through its operation. So by statically configuring port states like master slave and or disabled port state, you can achieve a very quick network timing startup, as well as no dynamic changes of link delays. The drawback, of course, is there is no automatic reconfiguration in case of any failure. So if the GM fails, since everything is steadily configured, you don't have a automatic reconfiguration to the next best available master. Another important features for achieving higher accuracy is physical layer synchronization. Now that is to synchronize the PTP clock layer within, for example, in synchronous Ethernet by referencing the PTP clock to the L1 clock. Why is this? Well, let's have a look at a typical setup or typical layout. We have grandmasters. We possibly have boundary clocks, transparent clocks. We eventually have a slave, of course, or multiple slaves. And through the PTP protocol, time is being transported across the network from the grandmaster to the slave. Of course, the grandmaster has its own clock reference, as have all the other instances. And now the time is being built according to the individual clock oscillators. And usually what has been done, these clock oscillators are controlled either numerically or directly by calculating the current offset and addressing this and accelerating or decreasing the speed of the local clock. Now, the layer which actually transports those messages, the layer 1, in synchronous Ethernet, for example, has its own clocking mechanism. The difference is that the clocks of the subsequent stages are derived from the synchronous or from the frequency which is running on the network. So that means that all these clocks on the physical layer are really synchronized to each other. The problem is that usually the PTP clock reference and the layer 1 clock reference are not the same in those individual devices. And that results in something which I have tried to simplify here. It's a bit more complicated in real life. I'm trying to simplify this as in a graphic. We have varying deltas or delays between the clock edges of the PTP clock and the L1 clock. So as you can see, we have stable clocks, PTP and L1, but they have a slightly different rate. So that means that we have a delta, let's say, on the rising edges of the clock, which is changing over time. It's getting bigger and smaller depending on how these clocks work to each other. Keep in mind, they are not synchronized to each other. So that results in minor deviations when it comes to timestamping with respect or in relation to forwarding the actual message, because the forwarding of messages happens with the L1 clock, but the timestamping happens with the PTP clock. And as you can see, there is a gap which is not static. And that prohibits or that inhibits a decent accuracy when it comes to, nanosecond or sub-nanosecond range. And in order to address this issue, what the White Rabbit group has suggested and has also implemented is that the clock reference for the layer 1 and the PTP is the same. So the grandmaster is referenced to the same clock as the L1. So that basically means that in this scheme, all the others follow the very same principle. And that means that both paths, the PTP time, or both layers, the PTP time as well as the layer 1, are absolutely synchronized to each other. They don't have to be, phase synchronized. It's not important, but they have to be, they are stable in synchronization to each other. So by linking the L1 clock as the reference to the PTP clock, now the deltas, which still may exist, are constant. And this is important because this constant offset can also be addressed, as you can see in one of the next slides. So this is just a complete picture, how this would look like. We have the PTP layer, we have the transmit clock layer, we have the level B layer, the backward path layer 1. And as you can see, it's important not that the clock edges are synchronous to each other, but that the frequencies are synchronous and that the offsets stay exactly the same. So that's the secret behind being able to achieve nanosecond accuracy. And with that comes the ability to configure a timestamp correction and any asymmetry calibration, which you may find in using various or different PHYs or PHYs for different media, which you sometimes will see in bidirectional fibers. So that is the other thing which has been added to the accuracy increasement. And all of this is being added or described in an added profile, which is called the high accuracy default PTP profile, which is also described in PTP version 2.1. Now, many words. Here's a summary for those who want to look at the presentation later on. It's just summarizing the points. The main point is everything is backward compatible to version 2.2, version 2. So all these added things are optional features. Any introduced version 2.1 device will perfectly work in a version 2 network. So the final question then remains, do we have a must-have for PTP version 2.1 for SMPTE 2110? Well, we can tell that the revisions which are coming out very shortly for 2059, 2110 are still referring to the PTP version 2 standard. Nothing is wrong with that. Neither 2110 or 2059 are broken by continuing to reference to PTP version 2. Everything works as it has been worked before. And current and future systems which are already existing or just to be rolled out into practical applications can still rely on the accuracy and reliability as provided by the PTP version 2.0. Some of the most useful features, that's my personal selection here, my personal evaluating of which are offered in 2.1 with respect to 2110, mixed multicast unicast operation for large network environment because it scales very well. We may see a value in modular transparent clocks because we now can set up cloud environments with tight synchronization. Profile isolation may come handy when we are working with different PTP profiles, as well as the interdomain interactions if you want to build very robust and reliable clocks. And security, of course, is something which sure also adds to 2110 and any media over IP technology. Slave port monitoring goes into the similar direction, so we can reliably and uniquely monitor what's going on in our slave clocks. And of course, when it comes to certain wide area network applications, the special PTP port feature might also come in very handy and useful because we then can take advantage of already existing, transport-specific timing capabilities. So how can we evolve towards PTP version 2.1? Well, the engineering way through system planning, PTP version 2.1 devices can at any time safely be added to the network without breaking the operation, and new features or improvements can be added, enabled as needed or supported. Of course, there's also the standards way of adding features through the 2110, 2059 drafting groups by careful evaluation of very useful features, introducing them into upcoming revisions, but of course, trying to preserve backwards compatibility wherever possible. So, summary, we have new features with version 1 of flexibility, robustness, accuracy, which may partly be beneficial for media system environments. All enhancements are fully backward compatible with the existing version. SMPTE 2110 and 2059 are not broken by continuing to reference PTP version 2. Current and future system can rely on accurately reliable operation. And so to answer and conclude on the presentation, answer the introductory question, the new revision of PTP is neither a must-have nor is a deal breaker. That's basically my summary. So I'd like to thank everyone for following me along. And as always, there's 1 minute overtime, I guess. And here's the special treat. Here's the special treat I have promised to you. Enjoy.
Die Krüge hoch, ein Prosit der Gemütlichkeit! Ein Prosit der Gemütlichkeit! Ein Prosit der Gemütlichkeit! Die Krüge hoch! Die Krüge hoch!